This hearing will now come to order, and I want to wish you a good morning and welcome to our subcommittee's hearing on one of the oldest and most important energy technologies available, advanced batteries and other storage devices. As long as people have been gathering energy or generating energy, we've had an interest in storing it because so often the rate at which we produce energy doesn't match the rate at which we use it. Also, there are times when we need portable power. We'd not be able to converse on cellular telephones, work remotely on laptop computers, or shine a flashlight where we needed it without batteries. As our distinguished panel of witnesses will discuss today, batteries not only or are not the only technology for energy storage. There are others that are not as commonplace, but have the potential to help us achieve a better match between energy production and energy consumption. Why is this important? Because renewable energy sources, wind and solar, do not produce energy on a continuous basis. These sources will become more viable if we can store the excess energy produced during times of peak wind and sun and release it as needed. Better energy storage technologies will also enable us to operate electric utilities in a more flexible and efficient manner. Energy storage can also help us respond to power outages more efficiently, providing greater electricity reliability. This could be vital for maintaining operations at critical facilities such as hospitals during a natural disaster. We're all aware of the high costs and delicate negotiations involved when building new electric generating capacity or transmission lines, especially when plants must be built to meet the power requirements of peak demand. With better energy storage options, we can expand our options for new electricity generation and transmission. Energy efficiency is the key to progress on three important goals: economic growth, energy independence, and a cleaner, healthier environment. New hybrid engines for vehicles have demonstrated how greater use of battery power can reduce fuel consumption and emissions. We can gain further fuel efficiencies and emission reductions, but this requires advances in battery technology and manufacturing far beyond what we see today, even in conventional hybrids. This would also allow for more advanced vehicles, such as plug-in hybrid electric vehicles, to enter the market and finally bridge the gap between the electricity and transportation sectors. With both stationary and mobile energy storage, we cannot let an opportunity to establish a domestic manufacturing base for these technologies pass us by. And unfortunately, we may already be losing that race. New R&D activities with the Department of Energy are critical to advancing energy storage technologies, and we should pursue this aggressively to ensure U.S. participation in this field. Chairman Gordon is working on legislation to support these programs at DOE, and the witnesses have been provided a copy of a discussion draft of that legislation. I look forward to their comments and suggestions to strengthen this bill and to accelerate our progress in energy storage technology. At this time, I'd like to recognize our distinguished ranking member, Mr. Inglis of South Carolina, for his opening statement.
Thank you, Mr. Chairman, and thank you for holding this hearing on the status of technologies that can accelerate the arrival of clean, renewable energy. General Electric manufactures wind turbines in South Carolina's 4th District. Inside that facility, as soon as one of the nacelles is finished, it's put on a truck and shipped out. GE tells me that the production line isn't slowing down. In fact, they're trying to add production capacity to meet increased demand, which is a very good thing for Greenville, South Carolina. These wind turbines and other technologies such as solar panels and vehicle batteries can speed the growth of our renewable energy sector. But the energy storage question is a significant hurdle that stands in the way. There's no doubt that we can cross that hurdle, and there's no question that it will be worth it. Getting over the hurdle means not just clean exhaust from our cars, but consistent and stable energy supply to the grid, even when the sun isn't shining and the wind isn't blowing. That kind of reliability is what's necessary before these sources become commercially viable as alternatives to oil and gas, both at our power plants and in our cars and trucks. I'm looking forward to learning from these two expert panels about how the federal government can help clear that energy storage hurdle. In addition, I'm also interested in fuel cells as batteries, and I'll return to that in question time. Thank you, Mr. Chairman, for this hearing, and look forward to hearing from our witnesses.
Thank you, Mr. Inglis. And now I'm honored to recognize the author of this legislation, Chairman Bart Gordon, for his opening statement. Mr. Gordon.
Thank you, Chairman Lampson. And I want to really congratulate you and Ranking Member English. You've had a very, almost a forced march first part of this year. Our ranking and as well as the majority staff have done an excellent job. You've turned out good legislation. And I hope this can be maybe one more element that we can put on the menu for an energy bill for the future. And so, again, I thank you for your past work, and I thank you for holding this hearing, ensuring that the United States is competitive in energy storage technologies. And I understand the witnesses have seen a discussion draft of the legislation I'm working on to accelerate the Department of Energy's energy storage programs, and look forward to your comments. Many of us here agree that energy storage technologies offer significant economic, environmental, and security benefits. A recent study from Lawrence Berkeley National Laboratory determined that the short-term power interruptions cost the United States economy over $50 billion annually. Strategic deployment of energy storage systems could increase reliability of the grid and reduce the impact of these outages. Energy storage systems can also enhance the use of renewable energy sources, diversify our energy mix, and lowering emissions. Broad deployment of energy storage technologies also can improve overall efficiency of the energy grid, or the electric grid. Storing low-cost energy generated at nighttime for use during high demand in the daytime makes sense. Energy storage is also critical for the next generation of vehicles, which will help reduce our dependency on foreign oil and lower greenhouse gas emissions. There is more work to be done to ensure batteries for electric cars are lighter, more powerful, and less costly. I also think that public-private partnerships can improve the production process for advanced vehicle components so that the U.S. becomes a leader in manufacturing these breakthrough technologies. With so many benefits of energy storage technologies, I think additional federal investment to research, test, and advance these systems should be a priority. And I'm very pleased that our ranking Member Hall has also been interested in these issues, and we look forward to working with him to accommodate his interest in getting a good bill together. And again, thank the witnesses for joining us today.
Thank you, Chairman Gordon. Acknowledge the presence of a number of other members of the committee, and I ask unanimous consent that all additional opening statements submitted by subcommittee members be included in the record. Without objection, so ordered. My pleasure to introduce our first panel of witnesses that we have here with us. First is Ms. Patricia Hoffman, who is the Deputy Director for Research and Development and the Acting Chief Operating Officer at the Office of Electricity Delivery and Energy Reliability of the U.S. Department of Energy, long title. Mr. Brad Roberts is the Chairman of the Electricity Storage Association. Mr. Larry Dickerman is the Director of Distribution Engineering Services at American Electric Power. And Mr. Thomas Key is the technical leader for the renewables and distributed generation at the Electric Power Research Institute. Welcome each and every one of you. You'll each have 5 minutes for your spoken testimony. Your written testimony will be included in the record for the hearing. When all 4 of you have completed your testimony, we will then begin with the questioning. And each member will have 5 minutes to question the panel. Ms. Hoffman, we
Mr. Chairman and members of the subcommittee, thank you for this opportunity to testify on behalf of the Department of Energy on energy storage technologies. The Department of Energy places great emphasis on the promise of energy storage and is researching a variety of storage technologies. Within DOE, applied research into energy storage technology primarily occurs within 2 offices, the Office of Energy Efficiency and Renewable Energy and the Office of Electricity Delivery and Energy Reliability. The Department is committed to developing technologies that can help advance President Bush's 20 and 10 plan, a legislative proposal to displace 20% of expected gasoline usage in 2017 through the greater use of clean, renewable fuels and increased vehicle efficiency. The development and use of plug-in hybrid electric vehicles, PHEVs, will help us work towards the goal of this plan. PHEVs represent a unique opportunity for the nation to transition from using exclusively oil, much of which comes from foreign sources, to fueling our vehicles, in part, with domestically produced electricity from the grid. High energy density batteries are key to the successful commercial deployment and development of these vehicles. Thus, EERE is researching lithium-ion batteries, which have 2 to 3 times the energy density compared to the nickel metal hydride batteries currently in use for today's hybrid electric vehicles. It is clear that plug-in hybrid electric vehicles will have impacts far beyond the transportation sector and become an integral, although not always connected, element of our stationary electric system. When considering the potential impact of widespread use of PHEVs on our nation's energy demand, it is essential to understand and address broader electric system impacts. For example, although ample generation capacity may exist on an aggregate scale to meet charging needs, how would PHEVs impact voltage regulation requirements? Or how would that generation capacity vary by region? Preparing answers today to questions such as these will allow PHEVs to successfully evolve from functioning solely as people movers to becoming stationary power sources for residential consumers to level loads and ultimately be a resource for the local utility. Stationary storage systems provide energy management, complement renewable resources, and can improve the power quality and reliability. This includes ride-through of power quality events such as voltage sags that range in length from cycles to seconds, often seen as the dimming or flickering of lights. Additionally, energy storage can be an uninterruptible power source providing minutes to hours of electricity, and as such, can be viewed as insurance coverage mitigating risk. Whether an energy storage device is paired with a renewable technology or simply installed alone at a residential, commercial, or industrial site, it can serve a number of valuable functions, acting as a balancing technology to solve intermittence issues, serving as an uninterruptible power supply, or leveling consumers' demand. Energy storage and photovoltaic hybrid systems, for example, would provide customers the flexibility to charge their storage device and discharge their stored power in combination with the PV system to satisfy their peak demand requirement. To date, large-scale utility applications of energy storage in the electric system have not been extensive. Roughly 2.5% of the total electric power currently delivered in the United States passes through energy storage devices and is primarily limited to pump hydroelectric storage. The percentages are somewhat greater in Europe and Japan at 10% and 15% respectively. The strategic placement of energy storage systems could provide load leveling within a regional control area, reduce transmission congestion, and provide ancillary services such as spinning reserve, voltage, and frequency regulation. Energy storage is just one way to increase the reliability and resiliency of the electric grid. When storage devices are paired with so-called intelligent smart grid technologies, the grid could fully take advantage of renewable technologies, allow for an increased number of PHEVs, and enable demand response. Like storage, smart grid technologies could have a revolutionary impact on our electric system. Smart grid technologies include smart appliance chips, advanced meters, and energy management systems located at the customer site. Intelligent agents and controls on the distribution system and wide area system monitoring on the transmission system are also considered smart grid technologies. The Department also recognizes that fundamental basic research into the future of energy storage materials and system is still required and can be a critical asset that accelerates our progress. One key opportunity the Department is pursuing is a new approach combining theory and synthesis of nanostructured materials, which have been identified as key to enabling the design of radically improved electrode architectures for superior power and energy density and increased lifetimes of energy storage systems. Portable electronic devices, which are enabled by batteries, are a form of energy storage, are now ubiquitous throughout society. When considering how widely accepted these devices have become in a relatively short period of time, one can only imagine the potential for storing energy at a much larger scale. Energy storage has the capability to reshape the way we fuel our cars, power our homes, and impact our nation's economic future. Federal investment in research, development, and deployment of energy storage technologies, in combination with innovative policies and infrastructure investment, has the potential to improve grid performance, reduce our dependence on oil, and promote our energy security, economic competitiveness, and environmental well-being. I am privileged to contribute to these research efforts, and thank you for the opportunity to testify today. This concludes my statement, Mr. Chairman, and I look forward to answering any questions you and your colleagues may have.
Thank you, Ms. Hoffman. Mr. Roberts.
Good morning, Mr. Chairman and distinguished members of this subcommittee. It's a privilege to be invited here today and given the opportunity to share views and perspectives of the Electricity Storage Association on the value of deploying energy storage in the grid of the United States. My name is Brad Roberts. I'm the current chairman of the Electricity Storage Association. This is a trade organization founded 17 years ago to promote the value of electrical energy storage in our nation's grid and other electrical systems around the world. ESA membership currently numbers approximately encompassing 100 organizations, which includes most of the major utilities in the United States, leading manufacturers of energy storage systems around the world, technologists from academia, engineering firms, plus potential investors in energy storage. Over this period, ESA has worked very closely with DOE's Energy Storage Program, Sandia National Labs, and various state agencies such as the California Energy Commission, the New York State Energy Research and Development Authority, and the Electric Power Research Institute, who is here today. ESA members have contributed key advancements to electricity storage technology using the very limited funds that have been available from DOE in the past. These activities have helped build a strong foundation for meeting the needs of a growing electrical grid that must now capitalize on the use of renewables sources and become more reliable, take advantage of smart grid technology, and be more resilient to threats of any kind. This brochure that was in the package that was given to you shows examples of storage projects done around the world by ESA members. Studies and projects funded by DOE and state agencies have helped define the most significant use of energy storage. The most compelling are help control power cost volatility, make more efficient use of fossil fuels like natural gas and oil to reduce dependency on foreign sources, benefit the performance of the transmission and distribution system nationwide, enhance the use of renewable energy sources and make them more dispatchable, help improve the overall performance of combined heat and power systems, improve the grid's stability, reliability, and security. Very large-scale systems like pumped hydro have been successfully providing bulk storage for the overall grid for some time, but only recently in the few years have practical and affordable distributed energy systems have begun to appear. Storage systems can capture low-cost energy at night and discharge it during peak daytime periods to help control price volatility. Storage systems can peak shave at the substation level and defer system upgrades. Small, fast-acting dynamic energy storage systems such as flywheels can provide vital ancillary services to the grid such as spinning reserve and frequency control. Wind energy generation at night can be transported on lightly loaded transmission systems to load centers and discharged at peak times the next day. Further, great amounts of electrical storage in the grid can provide protected power to vital assets in the community such as hospitals, airports, critical industries such as data centers, communications facilities, and on. As the amount of storage grows and these resources become more widely distributed, the entire grid will become more secure and less vulnerable to man-made or natural disasters. Storage has been identified as a critical component for the future of smart grids and will play a vital role in demand-side management programs and make them work more effectively. The groundwork developed by ESA members working with DOE and Sandia has identified that we can realize what we can realize with an expanded incentive program at this time. Many technologies have passed the proof of concept stage and are ready for commercial applications and will provide real benefits to the grid. Some of the recommendations we make are expand the scope and size of government funding storage programs that interact with the grid, provide incentives to national producers of storage systems and key sub-assemblies of those systems, provide funding to demonstrate the benefit of both large-scale and short-term balancing effects on wind power, provide funds to demonstrate the advanced storage to provide reliability enhancement for the grid, develop legislation to treat energy storage as a necessary component of renewable sources and provide federal financial support to incent end users to develop and deploy storage systems. Also ask FERC to require independent system operators to allow new energy storage technologies to compete in the commercial markets and take advantage of their faster response. Thank you for this opportunity to be here, and I look forward to your questions.
Thank you, Mr. Roberts. Mr. Dickerman, you may proceed.
Good morning, Mr. Chairman and distinguished members of this subcommittee. Thank you for inviting me here today. And also thank you for the opportunity to provide the views of American Electric Power on the significance of deploying energy storage to improve security, reliability, and performance of America's electricity infrastructure. My name is Larry Dickerman. I am the Director of Distribution Engineering Services for American Electric Power. American Electric Power is a 5 million customer utility in 11 states. We're one of the largest generators in the country, having 38,000 megawatts of capability. We are the largest transmission utility in the country with 39,000 miles of transmission line. We are the largest distribution company in the country with 207,000 miles of distribution. But of particular importance for the committee members here today, AEP is leading the utility in U.S. deployment of large-scale energy storage. Of particular note is a success. AEP installed the first ever megawatt-size scale NAS battery, sodium sulfide battery, in the Western Hemisphere in 2006. Based on our experience, AEP believes that storage has an important role in the grid of the future in that it can defer capital projects by improving utilization of existing assets. It can improve security and reliability. It can be deployed quickly, and it can work well with renewable resources such as wind. Also, we believe storage should be incented through mechanisms such as a federal tax credit in the range of 30% to accelerate widespread deployment. Over the last 100 years, AEP has been an industry leader in developing, advancing, and deploying new technology, and has always recognized the value of storage, as evidenced by our Smith Mountain Pumped Hydro facility. Over the last decade, AEP tested and evaluated the feasibility of new battery and supercapacitor technologies in our engineering laboratories. Based on those tests, AEP decided to move it from the laboratory and into further prototype testing with the sodium sulfide batteries for distributed energy storage system to support our grid. The major factors in selecting the NAS technology over alternative technologies were its safe and reliable commercial operation experience in Japan, compact footprint about the size of a double-decker bus, high efficiency and zero emissions, and you can relocate it if you need to. Based on successful laboratory and demonstration projects, AEP worked with NGK and with S&C Electric Company to deploy AEP's first commercial 1 megawatt NAS battery in 2006 on a 12 kV distribution feeder in Charleston, West Virginia. This battery can provide enough energy for about 600 homes for 7 hours. 600 homes for 7 hours. As a next step, AEP also recently announced a new initiative to deploy more energy storage on its system. And this initiative includes 6 megawatts of additional NAS-based energy storage by the end of next year, at least 25 megawatts of NAS battery capacity by the end of the decade, and adding another 1,000 megawatts of advanced storage technology in the decade after that. The aim of these initiatives is to achieve many benefits, including reducing peak load on lines and equipment, providing backup energy to improve security and reliability, offering shorter deployment time versus traditional solutions, complementing the modern grid concept, and enhancing the use of wind generation at peak demand. Although this technology in most cases rests on the distribution side, that's physically where it's at on a distribution system, other benefits of energy storage extend to all parts of the electricity infrastructure, including helping to optimize generation. The Department of Energy played a critical role in helping to deploy AEP's project in West Virginia by covering the one-time engineering costs that were needed for this first-of-a-kind installation in the Western Hemisphere. The partnership of DOE and AEP to deploy the first ever megawatt-sized battery facility in the United States was an ideal way of taking a new technology from research and development to real-world operation to accomplish something for a utility like AEP. Given the benefits of storage, AEP supports the continued development of storage technology and the adoption of incentives such as a 30% federal tax credit for deployment of distributed energy storage to accelerate the widespread use of storage to improve security, reliability, and performance of the United States electric grid infrastructure. Again, thank you for inviting me here today.
Thank you very much. Mr. Key.
Thank you. Good morning, Mr. Chairman, distinguished members. Representing the Electric Power Research Institute, I will focus on the role energy storage plays in the electric grid, both today and in the future. As a starting point, I want to recognize that electric energy storage is both valuable and expensive. Consider your retail electric rates at home that are around 10 cents per kilowatt hour, yet most of us will gladly pay dollars when we replace a battery in a flashlight, our cars, or portable appliance. We think it's worth it. And it is much the same way in the electric power grid. We are generally willing to pay more to store kilowatt hours of electricity than it costs us to make them by conventional means. The key is to have the energy in the right place at the right time, and this is an investment that we are willing to make. Today, energy systems delivers, our electric energy system delivers about 4,000 terawatt hours, and it runs with very little storage. I'd like to explain this. We are getting by without much storage because of the ingenious system of interconnecting many generators and consumers by forecasting demand, scheduling supply, and maintaining reserve generation as backup. If electric load turns off in one place, another one turns on somewhere else. In effect, we are running a massive just-in-time delivery system, and as we have seen, it can be tricky to keep the system balanced. We depend heavily on natural gas fire generation to both regulate up and down and to cover peak periods. Gas currently accounts for 47% of our supply capacity. Pump storage, our only significant method for electric storage, accounts for a little over 2%. In the future, we expect this situation to change. It will be increasingly difficult to operate this grid without additional energy storage. This change is our response to reducing carbon emissions, higher fossil fuel prices, and to enable more diversified ways of generating and using electricity. We will need more energy storage to support the new mix of lower emitting and less controllable electric supply, including solar and wind, but also nuclear and clean coal. We will need energy storage to enable a more effective participation by customers in managing their own use of electricity. One way storage can benefit the grid is to improve our use of the generators, the transformers, and the power lines. Currently, our utilization of these assets is below 50%. This is because of large variations in the electrical demand, day to night and seasonally, and because of our practice of just-in-time delivery. To find large-scale storage options, EPRI is looking at new ideas related in compressed air systems to supplement existing hydro. This will allow us to use existing transmission lines much more effectively. On a smaller scale, distributed storage using batteries, pumped water, or compressed air can improve grid asset utilization closer to the point of use. This is at a substation or feeder level. EPRI is working on a future smart distribution grid using distributed resources, including storage, to help manage electricity use. With more cost-effective storage technologies, we can increase efficiency and interact better with other new technologies such as rooftop photovoltaic and plug-in hybrid vehicles. These new storage technologies will be needed to enable future solar and wind by giving our operators more options in balancing renewable supply and demand. Cases are already documented where wind has challenged operators in New Mexico, California, and Hawaii. In all of these cases, storage is considered as part of the solution. I'd like to point out some challenges for electric storage related to economics and risks. Costs are very high, and siting and permitting can be difficult for large-scale storage. This is illustrated by the very modest amount of pumped hydro in the U.S. today. Energy storage, by its nature, creates value streams for several different stakeholders. With deregulation, it is difficult to aggregate the value and secure financing. This was illustrated by a compressed air plant that was not built to support West Texas wind in 2002. Distributed energy storage will require significant investment for development and demonstration. The utility industry is generally not in a position to make this investment. We believe that the DOE programs are on the right track to address the utilities' interests, and that there are many more opportunities in the future to partner on first-of-a-kind applications in different regions and under different grid operating conditions. In the future, EPRI will continue to work with its members in the Department of Energy to help realize the untapped benefit of new energy storage technologies in the electric grid. We believe that the expanded use of energy storage is important to improving the efficiency, reliability, and security of the electric power network. Energy storage applications in both the transmission and distribution grid will be essential to meet the growing demand for electricity using low-emitting technologies and gaining the full value of end-use energy management. Thank you, sir.
Thank you. Well, I appreciate the panel's testimony. We'll now enter into periods of questioning by members. I'll recognize myself as chairman for the first 5 minutes, and I would like to start with Mr. Roberts. The Department of Energy has designated 2 national interest electric transmission corridors, Mid-Atlantic area and the Southwest area. And these corridors include areas of growing population and growing electricity congestion. These designations have not been without controversy. Do you think that advanced energy storage systems could help reduce some or much of the need to build more electric generation and transmission lines?
Thank you, Congressman, Mr. Chairman. I think it's essential that storage be applied in the load centers, in the larger cities in those regions. It will help relieve that congestion in the peak periods, and will be very essential to making that happen and hopefully delaying those upgrades for a long period of time, hopefully.
Mr. Key, in your testimony, you state that another hurdle to energy storage deployment is the fact that the benefits are spread across a number of stakeholders, including power producers, system operators, distribution companies, end users, and society at large. Is there a role for the federal government to help bring stakeholders together to encourage investment in energy storage systems so the investment burden doesn't lie with one entity?
I think that we need help in that area. I haven't prepared any recommendations related to how the federal government might help, but it's very difficult to build large plants. And there is clearly benefits, aggregate benefits to the public to do this. We've seen that with our few existing plants that are so valuable today, and we're going to need more in the future.
Mr. Dickerman, in your testimony, you discuss what is needed to modernize the grid, including electricity storage devices and communication systems. In your opinion, do we need a new government body dedicated to facilitating or overseeing the modernization of the electric grid?
I think that clearly what's needed in this whole area is some clear thinking about how all this fits together. If I might take a minute, I think the kind of transition we're talking about here is very much like what happened with vehicles, where a vehicle in 1965 and one today is very different, and there's a lot of communication protocols, and there's a lot of computer capability, and there's a lot of control of various devices that have optimized an automobile today. Now we're talking this afternoon about the importance of storage and further optimization. It's a very complex thing that we're talking about doing in an automobile. An electric utility grid is far more complex in many respects in that there's so much of it. and it all operates together and it operates in real time. So we can improve the operation of the electric utility grid substantially with communication and with control and dynamic optimization and storage. But to do all that, there's a lot of technologies that have to come together, and it has to come together in a way that's common across the entire nation. And so I do think that there needs to be some kind of group that comes together to really work through what does this look like and how do the technologies work together.
Thank you. And for Mr. Robertson, Ms. Hoffman, several questions. As you know, power generators provide a number of ancillary services to the grid to help it meet reliability and operating standards. You both mentioned spinning reserves and frequency regulation requirements in your testimony as important ancillary services energy storage systems could provide to the grid. Ms. Hoffman also describes the department's frequency demonstration project in New York. In the future, do either of you anticipate energy storage systems playing a large role in providing vital ancillary services to the grid?
Mr. Chairman, yes, I agree that storage systems will provide a large resource for frequency regulation, voltage regulation, and spinning reserves in the future.
Mr. Chairman, I agree. One of the issues at stake here is today the response time for the generating systems to respond to frequency regulation signals can be 3 or 4 minutes, whereas fast-acting storage systems could respond in cycles, which would be more beneficial. It's stressful on many large plants to do this up and down regulation, and I think the power electronics that go with these types of systems adds VAR control, which is reactive power control, as a side benefit of providing real power. So there's a real opportunity here, I think, to take advantage of these devices to do those functions.
Ask these last two things together, and y'all just comment on them. Outside the Department of Energy's demonstration projects, are states or regions adopting policies to encourage the use of energy storage systems to provide ancillary services to the grid? And are there benefits to broad adoption of policies that encourage the use of energy storage for ancillary services for the grid?
Both New York and the California Energy Commission have strong programs in looking at energy storage demonstration projects, as well as some of the demonstration projects that you've heard here with AEP and the Electric Power Research Institute. I believe those are very strong programs in looking at the strategy for appropriate placement of energy storage systems.
I would agree with her comments. Those two states have taken a leadership role in this. I think other states are looking at how they might get involved, and I think the message is starting to spread around that there is real benefit here at the state level in the operation of the grids in those regions, and it's going to improve.
Thank you very much. I will now recognize Mr. Inglis for 5 minutes.
Thank you, Mr. Chairman. I'm particularly interested in the storage of energy for transportation purposes. And in the discussion draft we have before us of the bill that we may be marking up soon, we talk about research on ultracapacitors, flywheels, batteries and battery systems, including flow batteries, compressed air energy systems, power conditioning, electronics, manufacturing technologies for energy storage systems, and thermal management systems. I wonder if fuel cells are appropriately in that list. Ms. Hoffman, do you think so, or is a fuel cell appropriately in a list of batteries? It's essentially a battery, you just put something in it and then it runs through and creates electricity. Should it be in the list?
Fuel cell is a type of exchange, so for storing energy. It does use hydrogen as part of the fuel cell component. I will have to get back to you on that.
Yeah, it's just wonder whether it might appropriately be in there. Of course, you know, I've talked a lot about hydrogen, and I'm very excited about its potential applications to transportation. It's also true that batteries could be the competitor that wins a race to the car of the future. You know, if you have a really good battery, then perhaps you don't need hydrogen either burning in an internal combustion engine like BMW wants to do it, or in a fuel cell like General Motors wants to do it. And I was very interested in this story recently about Lynn Motor Company using an ultracapacitor. I think they're based in Austin, Texas, and maybe manufacture in Canada. I don't know if you saw the story, but they say that they have an ultracapacitor kind of concept that will enable a battery to be recharged in 5 minutes and to take a car 500 miles on a charge. Are you familiar with that? Or I read the article and I thought, wow, this could be fabulous. And then I saw some questions about whether it would really work. What do you have any thoughts about that?
I don't have any comments on your specific example. I'll have to get back to you for the record on that specific example. But with respect to your comments on the types of vehicles and what horse is going to win the race, I think diversity is an important aspect of having for our vehicle fleet as well as our stationary sources. And I believe that in that diversity, there are options for fuel cell cars as well as plug-in hybrid electric vehicles in providing the diversity that the country needs.
Yeah, and certainly it really doesn't much matter who wins the race, does it? I mean, as long as we can get away from what we've got now, which is a terrible way to get around in terms of the environmental benefits, the national security risk that we're running, and the job creation opportunity by creating these new technologies. So do you think that, I don't know if anybody else wants to comment on whether they've seen that, or looked at the ultracapacitor technology involving that car. Mr. Roberts, have you seen that?
Congressman, I've done some research. My company's done some research on that particular thing you read about in that article. And a lot of money's been invested in waiting to see when a prototype is finally delivered to see if these claims can be met, and because they're pretty broad.
Yeah.
And so it's kind of stretching the boundaries right now, but until some demonstration is done to see, we won't really know. I have a comment on the fuel cell usage in stationary application. Fuel cells work very well, but they have no energy behind them. They have no punch. So to make a stationary fuel cell really work effectively, you need to add some form of storage to it to give it the immediate energy it needs if there's a sudden load change or something. If you're applying it in an office building or something and the air conditioning turns on, the fuel cell can't deliver that surge of energy. And so storage actually enables fuel cells to work better.
Mr. Key.
Yes, sir. We have tested ultracapacitors and applied them, and I would just say that to drive the vehicle 500 miles, there must be some other fuel involved. It's just not enough energy, I think, today, although the research is very interesting in this area, and in fact, we've done a lot of it. Regarding fuel cells, I don't think that they're really treated as a battery or as a storage system. The storage, of course, is the hydrogen or the natural gas fuel that goes into the hydrogen. So I think one problem with treating a fuel cell, because it uses hydrogen as energy storage, is in fact we have used hydrogen in internal combustion engines, and from a tank of hydrogen. So there's a bit of a problem, I think, if you go down that route.
I might offer a couple of comments as well. AEP has been involved with supercapacitors, and we have not seen results anything close to that. But what we have seen is that they have a real advantage in the fact that they can go through a lot of charge-discharge cycles, and we don't even know the limits yet. We've not been able to wear one out. So it's very positive in that regard. In terms of fuel cells, I think fuel cells and storage, as Brad Roberts was alluding to, are really great marriage, because we are also working with fuel cell technology with Rolls-Royce 1 megawatt size fuel cells for deployment on a utility grid. And the thing about the fuel cell is it really likes to run flat out. In other words, you turn it on and you run it at a megawatt and it doesn't want to vary. If you put a storage device with it, then you can take up all the variation in load with the storage device. So a 2 megawatt unit, 1 megawatt of fuel cell, a megawatt of storage, and then you've got something that can sort of follow the load, and the efficiency of the fuel cell is very high. So I think it is an important technology related to this, and it's a technology that benefits from this.
Thank you, Mr.
Normally, I would recognize Chairman Gordon at this time. He has stepped out in the interest of conflict. Mr. McNerney, 5 minutes.
Thank you, Mr. Chairman. I want to thank the panel for coming in today with your testimony. Storage is, I think, critical to global warming issues because storage is going to allow us to utilize wind energy, solar energy, and other forms of intermittent renewable energies on a large scale. Right now, we're not able to do that because of the intermittency problems. So I want to see what we can do in terms of the federal government encouraging this kind of research. Mr. Dickerman, you mentioned, well, I'd like to know how you rate storage. Now, there's two ways to rate it: by the capacity, the installed capacity, so to speak, how much power it can generate and how much energy it can store, and then how would you use that how would you use that economically to decide whether a storage technology is viable for a particular application?
That's a great question. I think one of the issues with a technology like storage is that it's a fairly complex set of economics because you're talking about multiple benefits at the same time. So you can we can deploy a storage device to just shave a peak. So essentially what that gives you is about enough energy to serve 600 homes for 7 hours. If it's a megawatt, we're probably going to tend to be deploying more in the 2 megawatt size, so about 1,200 homes for about 7 hours. So that's the basic rating. You can use it for just peak shaving, and then in that case, it might defer capital like a new station transformer or line upgrades or things of that nature. But we are also working now to island the technology, that is to make it such that if you lose the feed to an area, a rural area, imagine a remote rural area with relatively poor reliability, single feed, you lose the feed because a tree comes across a line, then the battery can continue to feed that area. So that has a value as well. And then there's this value that is much harder for us to get our arms around that we were talking about, as it says there, a regulation value for generation and that type of thing. So there's several things happening at the same time in terms of building up the value. So each of the projects we're looking at, we're sort of tailoring the economics and saying how much do we save in terms of deferring capital because it reduces the load at peak, what's the value of the reliability that we're gaining, and basically those are the two factors. We're not really yet to the point of trying to decide what is the value of some of those other aspects that might benefit generation.
Well, that's right. With wind energy, which I'm familiar, you have, say, $1,500 a kilowatt installed, and then you have 5 to 6 cents per kilowatt hour produced. And I don't have a clear idea of how storage impacts those economics.
Specifically on wind generation?
Well, wind, but it would be, certainly the analysis would be transferable, I'm sure.
Well, in the case of wind, for example, wind can probably be best thought of as a negative load. So load is something that you can predict somewhat, and you can follow load with the generation that you've got. But the generation we're used to dispatching, you know what it is, you know you can dispatch it. If it's 100 megawatts, you know it's available, you turn it on and it meets the need. Wind generation, you don't know if it's going to be there because you don't know when the wind is going to blow. So there's an uncertainty. So it is uncertain in the same way that load is uncertain, and you have to follow load, and you also have to follow wind generation because you don't know what's going to happen. What the battery does is it enables you to store it and then make it available on peak when it means the most to you. And obviously the real price of producing energy goes up as the demand goes up throughout the day.
Ms. Hoffman, you had said something that piqued my interest, that we have 2.5% of our energy in this country goes through storage and 10 to 15% goes in Europe. What are the technologies they use in Europe that allow that high a percentage of their electric power to go through storage? How economic is that?
I believe I mentioned Japan. Japan did the first sodium sulfur battery, so they do have, it's the same suite of storage technologies that we are talking about here for the United States. And I'm sorry, I missed the other part of your question.
Well, what's the economics of that? How much do they pay premium for that storage capacity?
I will have to get back to you on that for the record.
Thank you. Thank you, Mr. Chairman.
Well, the storage in Japan and in Europe is pump storage, sir. There's very little battery storage, you know, that would add up to percentages in the world.
Thank you, Mr. Chairman.
Thank you, Mr. McNerney. Ms. Biggert, 5 minutes.
Thank you, Mr. Chairman. Ms. Hoffman, what are the origins of the NAS battery technology? I thought that this technology was developed in the United States, and did the government play a role in that development?
I'm going to defer to Mr. Dickerman.
Okay, Mr. Dickerman.
The NAS battery technology was developed in 1965, and Ford Motor Company was involved. And it was a technology that, of course, was considered at that time as having possible application in vehicles. It was taken to a certain extent, and basically the technology then was picked up by the Japanese, and a combination of NGK with support of Tokyo Electric, the Japanese government, continued to develop it and brought it to the kind of maturity to where it could be used in the Japanese electric grid infrastructure.
Was it ever used by the government, do you know, or Department of Energy had any research on that?
That I don't know.
I guess I'm just wondering, because it seems like this is another example of where technology was developed in the U.S. and then commercialized and deployed by foreign companies and governments, just like we've developed the nuclear technologies, particularly the recycling, and then it's been commercialized by France, and now they're selling this back to the United States. So. And we're having to buy from overseas because we've failed to capitalize on the inventions and the technology here. So, do you have anybody have any ideas about how to prevent this, how we can make sure? Mr. Roberts?
Sure.
Oh, I'm sorry.
I'd like to comment on that. Yeah, that part is true, but taking that battery energy and delivering it into the grid requires very sophisticated power electronic equipment, and we are in a leadership position in that field in the United States, and we've been very fortunate that we've developed that marketplace, and we're one of the leaders. My company is one of the leaders in that arena, and our initial developments and all of our work are a very good example of DOE programs that go back about 10 years ago. So,
Mr. Dickerson?
Yes, I think there's really 4 stages to development of any technology. There's the basic research, and quite often that involves academic institutions, pure research kind of programs in various places around the country. Then there's applied research, where you start thinking about what you can do with it. Then I think where things tend to break down is there's a need for demonstration projects, and at that point you need to take the technology from something that's applied research like we did with this NAS battery, or like we're doing with the islanding aspect of the NAS battery, and actually do something that has to work and actually serve a useful purpose. And at that point there needs to be a greater collaboration between industry and between the organizations that are doing the research and understand the technology to create the real handoff as to how can you use this technology in a real way to accomplish a real purpose. And then once that happens, I think there has to be incentives for widespread use. And what happens is quite often the technology initially, even if it works, is at a price point where it really isn't competitive yet. and it needs an incubation period through some type of incentive. So basic research, applied research, demonstration projects, incentives for widespread use. I think that's what's needed, and where things break down is in the demonstration project phase with industry, I think.
But why did AEP then need DOE's help when deploying that technology here when it was in use for 15 years in Japan?
Because it had not been deployed on a U.S. infrastructure, and the U.S. infrastructure had some fundamental differences in the power electronics that Brad Roberts was talking about. And our vision from the start was to take it to a different level. So in Japan, the technology just sits there and peak shaves. And to even do that, we needed to develop the technology further to apply it on a U.S. system. The thing that hasn't been done anywhere in the world is to island this kind of a technology so that it can improve reliability and function with no connection to the electrical grid. That we're doing for the first time in the United States, anywhere in the world.
And Ms. Hoffman, in your testimony, you talked about replacing oil, imported oil, to use domestically produced fuel, electricity to fuel our cars. But if we continue to, in a country, that trend of not encouraging gas or coal or nuclear for our electricity energy, and not allowing drilling for natural gas on the outer continental shelf or in ANWR, don't we run the risk of being more dependent on foreign countries for natural gas? It seems like so much of this is based on natural gas, which is really a commodity that we will run out of, and I think we need to keep it for, you know, the things that are really plastics and fertilizer and things that we will always need to have that.
Thank you, Congresswoman. The department is looking at advancing all the generation types that I think the United States is going to require in the future to meet that demand for electricity, and we'll continue to look at clean coal concepts, advanced nuclear, and renewable technology to the maximum extent possible.
Thank you. Thank you, Mr. Chairman.
You're welcome. Chair now recognizes Ms. Giffords for 5 minutes.
Thank you, Mr. Chairman, and thank you to our panelists who's come in today to talk about energy storage technologies. I'm excited, Mr. Chairman, about this topic because when I think about the challenges that we face as a nation and that the world faces, I think a lot of solutions to our energy needs can be talked about here in this room and hopefully put into action in terms of policy. This technology is important not just because of global warming, but because of our dependency on foreign oil as well. And figuring this piece of the puzzle out is going to be critical. I'm also really concerned, and Congresswoman Bigger talked about it, is this competitiveness issue that we're facing. We put money into research and development here in the United States, and then we see that technology furthered in other places. And that's got to change. And hopefully this Congress can be part of making that a reality. A couple of questions. I'm from Arizona. Everyone here on this committee knows because I always talk about Arizona. I'm very proud of my state. And one of the beauties that we have in the state, of course, is our abundant supply of sunshine. We have over 350 days of sunshine every year. So it's really solar energy that has the greatest potential for renewable energy in Arizona. I noticed, Ms. Hoffman, in your written testimony, and even in the testimony provided by the other panelists, that there was no mention of thermal storage technologies. And that's obviously going to be critical for the development of solar power. So I was hoping that you would talk about this form of technology, what the Department of Energy is doing, and in each of your individual respective areas, where you see thermal storage development coming from, and whether or not these applications can be used in other areas besides the concentrating solar power, which we're seeing developed out in areas like Arizona.
Thank you, Congresswoman. Thermal storage is an opportunity, and the department does not currently have any research programs in the area of thermal storage that I'm aware of. I will check on that and get back to you for the record. But it does have potential for residential usage for thermal storage, and it can provide a balance with your photovoltaic system. So,
wait, Mr. Chairman, Ms. Hobbs, let me clarify. So you're not aware of DOE having any research or any development into this area?
At this time, I will check for the record, yes.
A comment on solar energy and storage. Typically, around the country, solar energy peaks 2 to 3 hours before the load peaks. And if you apply storage, you can capture all of that energy and extend it into the evening and take advantage of that sunshine that was shining brightly in the afternoon when everybody was still at work. And so that's one of the areas storage can level out solar energy and extend that peak period to meet the peak period of the actual load itself.
Thermal storage is of great interest to a number of our members in the West because of concentrating photovoltaic. In fact, we expect as much as 5 gigawatts of that type of generation, and the thermal storage is a very natural part of a power tower, and it's also being looked at and tried out for the trough technology. It's limited pretty much to the Southwest. It's great, and it will be a big help with solar and in fact just balancing that the Western system, which is has such long distances and issues with stability.
Congresswoman, I will clarify that there is a thermal storage with concentrating solar power in our energy efficiency office. I will have to get back to you with more details on that program.
If you would, please, because, Mr. Chairman, you know, here again in Arizona, you have an area with large tracts of land, terrific sunlight, and also the scientists, University of Arizona, and other research institutions as well. The University of Arizona just announced a specific program that's going to go basically a Center for Solar Excellence that will be developed. And I think if we use that technology, we use the resources we have, we're able not just to help the fastest growing state in the nation, but also export that energy as well. Let me just switch to another topic really quickly, which is the environmental impact of the storage technologies in general and batteries in particular. You know, as we try to develop more and more of this technology, and again, in a state like Arizona where we have a lot of hard rock mining and a lot of the environmental impacts, I was just hoping that the panel could address the ability to recycle this technology and also the increased demand for some of these precious and rare metals that are going to go into the storage capacity.
I'll start the responses, Congresswoman. All of the technologies, the battery technologies that are being used today are based on 100% recycling taking place at end of life in those technologies. That's something that's very important. The sodium sulfur battery is a hermetically sealed box, so there's no emissions associated with it. And so at the end of its life, it's totally recycled.
And for the years of operation in Japan, there haven't been any environmental or safety issues. Most of what's in that big box the size of a double-decker bus is sand, and that's most of the weight. But there really aren't any environmental issues that we've seen. And as Brad says, at the end of life, we expect to recycle the components.
You're welcome. Recognize Mr. Bartlett for 5 minutes.
Thank you very much. I must apologize for being called out for some of your testimony. I was really interested in hearing it. With 10 kids and 16 grandkids and 2 great-grandkids, I ask what I think is a rational question to those who would like to drill in ANWR and offshore. If you could pump ANWR and the offshore tomorrow, what would you do the day after tomorrow? And there will be a day after tomorrow. Wantonly consuming the small additional reserves that we have is not a prescription of security for tomorrow. Mr. Key mentioned the challenge that we have in getting batteries for cars that will get us very far. And that, of course, is because of the incredible energy density in our fossil fuels. 1 gallon of gasoline, little, still cheaper than water in the grocery store, carries my Prius car 50 miles. How long would it take me to pull my Prius car 50 miles? This is incredible energy density. And to provide that, even anything approaching that energy density in batteries is a horrendous challenge. And that's why this is such a difficult challenge. You know, in our aspirations for the future, we really need to be rational. And 20 in 10 is not rational. There isn't even a prayer unless we have a devastating worldwide depression with demand destruction that we can even come close to displacing 20% of our gasoline in 10 years. That is not going to happen. If all of our corn was used for ethanol and discounted for fossil fuel input, it would displace 2.4% of our gasoline. If all of our soybeans were converted to diesel fuel, they would displace 2.9% of our gasoline. Those aren't my numbers. Those are National Academy of Science numbers. And if we use all of our wastelands to plant to a mixture of grasses and use the current hype, the cellulosic ethanol, that might produce as much displacement of fossil fuels as all of our corn. So you add up these three things, and you're way short of even 10%. You know, I'm all for doing something rational, but, you know, this is an impossible dream, and I don't want to set us up for disappointment. We're going to be enormously disappointed if we think that we can even come close to displacing 20% of our gasoline in 10 years. We can certainly reduce by far more than 20% of our consumption of gasoline in 10 years by conservation. I was in France at the last election. By the way, it's interesting that the new French president is the son of a Hungarian immigrant. He's doing a pretty good job, isn't he? And I looked there for people riding in a pickup truck as personal transportation. I saw not one. And I looked for people riding in an SUV. The only SUV I saw in Paris was parked behind a church. I did not see one on the street. If we really want to reduce our consumption of gasoline, we need to approach it rationally, not with some impossible dream of continuing to drive these huge SUVs and pickup trucks, one person in them, for personal transportation and displace 20% of our gasoline in 10 years. Am I wrong?
I think I'd like to, Congressman, make one comment. I think everybody agrees that conservation and changing our ways has to take place. Along that way to that process, we need to use the energy resources we have much more efficiently. We're adding a lot of wind into the system, and to try to utilize it more effectively as quickly as we can. These programs that are listed in this bill, I think, would go a long way to helping that. But the real problem is, I think, as you suggested, in that things have to change and attitudes have to change.
I'm a huge fan of wind and solar. I have an off-grid home. All of my electricity is produced by wind and solar. And I have a big bank of lead-acid batteries to supply. But you must be very frugal in the way you use electricity if you're providing for yourself. There's nothing that will make you a better convert to conservation than producing your own electricity with wind machines and solar panels, and watching how quickly that disappears if you're at all profligate. Thank you all very much for your testimony, and you're helping to move us forward. Thank you. Thank you, Mr. Chairman. I yield back.
Thank you, Mr. Bartlett. Chair now recognizes Mr. McCall for 5 minutes.
Thank you, Mr. Chairman. Roscoe, I want to congratulate you on 10 children. I have 5 children, but you've managed to double the amount that I have. That's an incredible accomplishment. I want to pick up on an issue that was discussed earlier, and that is solar. My home state of Texas also has a lot of sunshine. Applied Materials in my district is working on solar panels, making great progress with those. And the real issue is storage. As you know, they tell me that the power grid can be used to, that's sort of their theory where they're going with all this, is to store the solar energy from the panels into the power grid and then be able to draw upon the power grid. In other words, sort of getting credits for that. Is that a realistic technology? And anybody can answer.
Well, I think that is what we were saying. The complement of storage in wind is that you simply are taking it from something where you can't be sure when it's available, and you're storing it and making it available on peak, which clearly has a value. It sounds like that's exactly what they're talking about doing with the solar, and so it's the same value proposition, simply making sure that it's available and a dispatchable resource on peak when needed most.
Mr. Key?
The point that we'll use the electric grid to buy and sell, to trade solar and wind energy is critical. As I described in my testimony, we're limited, I think, in doing that, especially as we take our regulation type generation, natural gas, and we try to move toward more nuclear and clean coal, and we add wind, and then it's going to be more difficult to do this trading and keep the system in balance. So I think it's a correct statement, but it's a matter of how long we can continue to do that as these renewable resources come into play.
And Ms. Hoffman, as I recall your testimony, you're not aware of any thermal storage research and development programs at the Department of Energy?
Congressman, I was actually thinking of ice storage and some of those technologies when we were talking about thermal storage. We do have a concentrating solar power program that is tied with thermal storage, but I will have to get back for the record on details of that program.
Okay. One more of limited time, the hybrid plug-ins. You know, we have hybrid vehicles, we have batteries. Why? Just explain to me, I'm not a scientist, why it takes so long to get a hybrid plug-in vehicle that could be available to the average consumer, if anybody knows the answer to that one.
The next panel may be able to address that with the transportation.
Ms. Hoffman, you'd probably be the best person to try to venture at that. I won't be around for the next panel.
From the department's perspective in developing a vehicle, there is a development cycle that the manufacturers have to put plans for future vehicles, and I understand that cycle is somewhere around 8 years to 10 years. And so they're looking at now for technologies that they will introduce in the marketplace at a later time frame. For the record, I can find out more on the development cycle development for introducing new technologies into vehicle applications.
I know we've sponsored legislation for tax credits for that. It just seems to me that that should be more in the short term than long term. And finally, Ms. Hoffman, have you had a chance to look at the proposed legislation before us? There are two sections, sections 6 and 7, that deal with demonstration projects at the Department of Energy. Can you comment on these two sections and also whether there is any duplication between these two programs?
From a technical perspective on the content of I think it's very synergistic to where the department is heading, where the states are heading, and where other research programs are going for the types of demonstration projects. So for an area of completeness, I think the bill does capture both of those aspects.
So you see them as complementing, not duplicating. Is that fair?
Yes, sir.
And finally, intellectual property is going to be a real issue if advanced technologies are discovered through these joint activities. Do you have any thing in place to protect intellectual property?
The department does, and I would have to get back to you for the record on that one.
Okay. That'll be fine. Thank you, Mr. Chairman.
Mr. Aiken, I recognize you for 5 minutes.
Thank you, Mr. Chairman. I didn't know of the different witnesses. Do we have anybody that's on top of where we are in terms of battery technology and that developmental process? My background's in engineering. My sense is that maybe one of the shortest paths to solving some of the dependence on foreign oil is using the off-peak power from the whether it's coal or nuclear generation, and being able to put that right into a car. Also has the added benefit of not paying any fuel tax, which I like. But anyway, what's the status of battery technology? I understand basically the answer to my friend's question here is that it's too expensive. The batteries are too expensive. They don't last that long, and just economically, it's cheaper to burn gas. But the question is, where is that technology? Because certainly it's come a long way in 10 years. I mean, I remember when they came out with that first electric-powered, screw gun or drill, and the thing was not much power to it. Now they've got, these big hammer drills all running on batteries. Or is that continuing to move or not?
Congressman, Unfortunately, in the afternoon session, there's a battery manufacturer that's here that could address that probably a little better. But there's a lot of activity in research and development of advanced batteries, particularly for vehicle application, going on in this country right now. And
But that's not your expertise particularly?
No.
Okay. Well, that's all I had for questions. Thank you, Mr. Chairman.
You're welcome. I think everyone has had their opportunity to ask questions, and we do have a second panel. We want to thank you very much for coming. I will, in closing, ask, are any of you aware of anything that has to do with wireless transmission of energy? And if so, I'd like to talk with you. Again, I thank you all for coming. We'll take a short break. We'll be in recess before our next panel comes up.
Huh?